A crime has been committed, and there were no witnesses. Will this crime be solved? Will the criminal be apprehended and convicted? This is a job for science. For this crime, like many thousands of others, will be solved in the laboratory by scientists using the principles of virtually all of the physical and biological sciences. The evidence is here, some obvious, some unseen. But the scientist, the criminalist, will use every bit of it to supply facts which will identify and convict the criminal. For today, the science of criminalistics has become a powerful weapon in the war against crime. The field of criminology includes all aspects of crime detection and law enforcement. But the science of criminalistics deals only with the role of scientific evidence in the administration of justice. When a crime has been committed and the criminalist becomes a part of the investigatory team, all the principles and techniques of science are concentrated on the evidence. An outstanding scientist in this field is Dr. Paul Kirk, criminologist, crime consultant, and one of the country's best-known expert witnesses at criminal trials.
Criminalistics is both a profession and a scientific discipline. We are concerned with the study of physical evidence, that is, physical objects and physical facts relevant to the crime from which a reconstruction and understanding of the crime may be developed. Everything can be evidence: organic, inorganic, biological, manufactured, just about anything on Earth or in the air. As yet, we've never had to deal with evidence from outer space, but we probably will someday. Whenever possible, we like to collect the evidence ourselves at the scene of the crime. We must try to find all of it that is relevant, and collecting it so that you don't damage it or contaminate it is a specialized task that often requires special equipment. Some of the evidence at the scene of the crime would be obvious to anyone, but for some of the most important clues, only an expert would think of looking for them or have any idea what he could learn from them in the laboratory. And you'd be amazed at what these tiny witnesses to a crime can tell us under a microscope.
How do you learn to be an expert, a trained, qualified criminalist? Dr. Kirk is the authority who can answer that question, too, for he's a scientist, a biochemist, as a matter of fact, who wears two hats, crime consultant and professor of criminalistics at the University of California's School of Criminology. This school on the Berkeley campus is unique in the United States because there aren't any others like it, and students come from literally all over the world for study and research.
This morning, class, we're going to consider the question of the comparative value of different types of evidence, and we're going to use one specific case to illustrate it, in which there are four types of evidence. That is, there is glass, wood, a blood stain, and hair. Those four. We have a suspect in custody who must be released within some 30 hours or arrested.
Before you can get into the school, you have to have a solid foundation in general science, because the more you can learn about chemistry, physics, biochemistry, botany, biology, immunology, organic chemistry, toxicology, and the other related scientific disciplines, the better criminologist you'll turn out to be.
Tom, what would be your order of this evidence under the conditions?
In this case, where speed is of the utmost importance, I would first examine glass and blood because they are relatively the fastest to examine. Thirdly, I would examine the hair, and last of all, wood.
And would you rate the order of the value of the evidence the same way?
Well, I would value glass and hair about equal, with blood following in the third position and hair being rated as least valuable of the four.
Why would you put glass and hair as the equivalent value?
There's much to learn. You can get some of it from textbooks and in class discussions, but the real things that you're going to do as a practicing criminalist are accomplished in the crime lab with your hands and your eyes. And the students keep the school labs busy from early morning until late at night. They don't work with real evidence from actual cases because it is retained by the district attorney even after a case is solved and closed. But samples of all kinds are provided, and the students perform both physical and chemical tests to examine and identify thousands of known and unknown materials. How is a crime solved in a lab? What can you learn from a single strand of hair, a bit of fiber or metal, a tiny fragment of glass, or a drop of blood?
Blood is one of the most frequent and important types of evidence encountered in criminal investigation. And we find it at the scene of crimes of violence about 95% of the time. When we find a visible or an invisible stain, we take it to the laboratory to find out if it is blood. There are several very sensitive and rapid catalytic tests we can use to find out if a drop, stain, or smear is blood. Of these preliminary color tests, the most widely used is the benzidine test. It works with extremely minute quantities of blood, and it's an excellent presumptive test. The stain is blood, but is it human or animal? We can find out the origin of blood by a simple test often used by immunologists. It is based on the fact that an animal normally can tolerate only its own types of proteins and employs the same type of reaction effective in natural immunity to disease. The serum of the blood of an animal which has been immunized to human blood is layered with a little of the question blood. If a precipitate forms, that is a white band at the interface, it's proof that the blood is from the same origin or species as was used to immunize the animal. A properly performed precipitin test will give positive proof of whether the blood is human or animal.
A spot of blood may help to convict a criminal or exonerate an innocent person when it is tested to determine its international blood group. There are 4, known as A, B, AB, and O, and everyone's blood is in one of these categories. In the United States, only 3% have AB type. So if the sample is type AB, about 97% of the population can be eliminated as suspects. With other tests, the drop of blood can be individualized even further. Since identification is essentially a matter of elimination, with each specific step, more and more people can be ruled out, until ideally you end up with the one and only person who could have possibly committed the crime.
By use of electrophoresis, the protein distribution of the blood can be checked and compared with other specimens.
Having placed a drop of the sample on paper strips, an electric current is applied to them. After the strips have dried and been stained, the protein distribution of the blood can be compared with other specimens.
Going one step further, we can test blood for differences in immunological characteristics. For example, immunity to measles.
After separating the proteins by electrophoresis, antiserum is applied to the strip. The antiserum diffuses into the separated blood proteins. Precipitin arcs are formed as a result of the precipitating activity of the antiserum. These arcs may be compared to show possible differences between individuals.
No two individuals have the same kinds of immunity in the same proportion. By learning more about the composition and behavior of blood, we eventually expect to be able to identify an individual by his blood as certainly as by his fingerprints.
One of the most important parts of a criminalist's training is learning to recognize common material or microscopic evidence found at the scene of the crime.
It is virtually impossible for a person to commit a crime without leaving microscopic evidence behind and carrying microscopic evidence away. This evidence may be the only clue to the criminal's identity, and frequently it's the only conclusive proof of guilt or innocence. Microscopic evidence is largely obtained from the filter of the vacuum sweeper used for collecting debris from crime scenes and especially from clothing. The material is placed under the stereoscopic binocular microscope where the sweepings can be readily scanned or minutely examined by teasing the mass apart with dissecting needles. We use this microscope to examine 95% of our evidence. You might say it's the beginning of all good laboratory procedure. Each particular type of evidence is picked out with fine-tipped forceps and placed in the individual sidewells.
What can you learn from a pile of sweepings that will help you find a criminal and solve a crime?
How are things coming along, Mary Lou?
I've been making some progress. I've sorted out all the things I think will be significant as evidence. For instance, there's some textile fibers, some metal and wood fragments, some paint chips and glass fragments, and some hairs which may turn out to be animal or human. Perhaps the most important thing I found is something that looks like marijuana.
The study of microscopic evidence requires patience and perseverance blended with skill and experience. But the rewards make it well worth the effort. Microscopic evidence is capable of proving facts of great significance, and no attorney, no matter how clever or dramatic, can ever obliterate the effect on a jury of one proven and significant fact.
Microscopic particles of hair and fibers are important clues in many criminal investigations. They cling to garments in spite of careful brushing or cleaning, and they can be found in cuffs and pockets which appear absolutely clean. Sometimes they can be authoritative witnesses to the identity of the criminal.
Fibers of unknown origin will ordinarily be obtained from clothing, sweepings, or from the locale of the crime, such as the windowsill, or edges of broken glass, nails, or other irregularities that have snagged clothing or other cloth objects. They may be found when there is no other significant evidence. A criminologist must be thoroughly familiar with the identification of common textile fibers. Cotton, for example, is a flat fiber showing a characteristic twist similar to the appearance of a twisted ribbon. The cellular structure is readily seen in most cases. Wool is characteristically a hair, usually showing no medulla and with very noticeable transverse scales on the narrow fibers, ranging to almost complete absence of visible scales on the large fibers. These scales give to the edge of the fiber a characteristic notched appearance.
Hair is a tiny but telltale clue that can usually be found in connection with half of all the crimes committed. But what can you learn from a fragment of hair that will help you describe and identify a criminal? Under your microscope, magnified many times, a hair may reveal these facts, whether it's human or animal, and the species of animal. If it's a human hair, the race and probable sex of the individual, whether it fell out or was torn out or cut off, the part of the body from which it came, the natural color, or whether it was bleached or dyed, and the treatment it received from the barber or hairdresser.
Our criminalistic students examine many samples of hair to determine origin and characteristics. Basic to their examination is microscopic analysis and scale counts.
Glass fragments from a broken window are found at the scene of a crime. A minute glass particle is found embedded in the sole of a suspect's shoe. Is the glass identical? Is this the criminal? Glass is a very complex material with many variations in composition.
The chemical variations occurring in glass are reflected in differences in their physical properties. One of the physical properties which is useful in comparing glass fragments is density. Few substances have exactly the same density. Therefore, different samples will settle to different levels if dropped into a column of liquid which is of gradually diminishing density from bottom to top.
The principle was discovered by Archimedes sometime before 215 BC, but it was adapted for criminal investigation work by Dr. Kirk.
It is allowed to stand for 24 to 48 hours until the liquid levels merge to make a uniform gradient. Then the two bits of glass are dropped into the top of the tube. They slowly settle to points which correspond with their own densities, in this case to the same level, indicating a possible common origin.
Did the glass in a suspect's shoe come from the scene of the crime? Guilt or innocence may depend on the criminalist's findings. So the glass particles will be subjected to other tests as the careful investigator seeks absolute proof of common origin. You can find some of the answers with microscopes and test tubes. But the criminalist also uses many intricate electronic and optical instruments to probe the mysteries of the many materials and substances he must identify and compare. And the students spend many long hours learning how to use complex equipment like this, which can be used to perform almost any electrometric or photometric measurement.
The spectrograph is one of the workhorses of the crime laboratory for analyzing paint chips, metal fragments, soil comparisons, and all types of small bits of mineral evidence. It is based on the principle of emission spectra and is an ideal instrument for studying the identity of metals.
The experiment is to compare an unknown metal sample with a sample of known origin. Is a particle of metal found on the floor by a burglarized safe identical to the one found in a suspect's pockets? The method for comparison is based on registering photographically the spectrum of each of the samples.
When any element is heated to white-hot intensity, the light which it emits will produce a spectrum distinctive for that element. No two are alike. The lines and bands are different colors and in different positions. If two samples yield identical spectra in all observable particulars, there is no doubt that they have identical chemical compositions.
Infrared absorptometry, very familiar to the chemist, is now being used extensively in the crime laboratory for individualizing organic materials.
The infrared spectrophotometer will identify any organic substance or mixture of compounds such as paint or plastics by drawing a chart of the sample's absorption of infrared light. We sometimes call it the fingerprint technique of chemistry.
The students in criminalistics work hard. They have much to learn. Study the facts. Practice the laboratory techniques. But most important, develop a scientific attitude. Use your imagination, ingenuity, and curiosity. But balance them with skepticism, common sense, and conservatism in your interpretations.
To be a good criminalist, you need a broad scientific background. Every natural science you can study will be valuable to you. And you should, in addition, adopt the permanent attitude of a student, because you never will know all of the useful things that can serve your purposes. In criminalistics practice, mistakes are not allowed. Testimony once given cannot be corrected by giving it a second time. And as an expert witness, you have to learn how to popularize science so that the jury can understand your testimony.
When you're in school, it's just an exercise, an experiment. But someday you'll be facing the real thing, when a man's guilt or innocence, his life or freedom will depend on your findings. A crime has been committed, and there are no witnesses to describe the burglar, to identify a suspect, to testify and convict the criminal. Or are there? A window glass has been broken inward, and its fragments litter the floor near the point where the entry was made. The lock area on an inside door is scratched and scraped, apparently by some sharp tool or jimmy. Near the jewel case, a dirty handkerchief shows reddish stains. An old gray jacket, size extra large, is found in a corner near the case. On the jacket and in the pockets are several blonde hairs, blue cotton fibers, earth, sand, gray crushed gravel, bits of hay and straw, and feather fragments. That's the evidence. Can you describe the burglar, tell the police where to find him, and what evidence to look for on a suspect? There are many tiny witnesses to the crime, and science will get them to testify. Description: male, Caucasian, height 6 feet, medium build, straight blonde hair, cut on the right hand, possibly wearing a blue cotton shirt and brown wool pants. Probable occupation: a laborer associated with building construction. He lives outside the town proper on a small farm or garden plot, raises chickens, and keeps a cow or horse. When a suspect is apprehended, check for glass and metal fragments in shoes and clothing, and blood type AB. In criminal investigation, there are no pat answers. You never get asked the same question twice. Each case requires a new approach, a different technique.
The thing you need most is judgment, balance, experience. And some of it you have to learn the hard way.
Crime is perhaps the oldest problem that confronts mankind. But experts in criminalistics, like Dr. Paul Kirk, are finding revolutionary new ways to bring the guilty to justice and remove the shadow of suspicion from the innocent. Thanks to Science in Action in the Crime Lab.